Hi everyone, Mr. Chaffee here for our next lesson on systems of equations. Today we're going to be learning a bit about matrices and how we can use them as a tool to help us solve various systems of equation problems. To do so, we're going to need a little bit of background information on matrices and some of the properties that they have. Let's get started taking a look at a definition for what a matrix actually is. So we can say an m by n matrix is an array of m rows and n columns of real numbers. Each entry is labeled as A sub ij to describe the location in row and column position. Now let's see what that looks like, taking a look at a couple of example matrices here. So we have a generic matrix on the left-hand side filled with our variable terms of A sub ij, where we have our rows go along the left-hand side. We have 1, 2, 3 rows, and our columns go vertically up and down. We have 1, 2 columns here. And as you can see, my first entry is A sub 1, 1 because we're in that first row and that first column. So we're position 1, 1. If we move over, we're still in the first row, but now we're in column 2. So we're position 1, 2. And as such, if we move down, we're in the second row, first column. This entry is A sub 2, 1, and so forth as we move throughout our matrix. And this is called a 3 by 2 matrix because we have 3 rows and 2 columns, 1, 2. Where normally we'll have our variable terms A sub ij as real number entries, like I do on the right-hand side here in this matrix. So now we have a 2 by 4 matrix because we have 1, 2 rows, and then our 1, 2, 3, 4 columns. So these are what we're more so typical of what we'll be working with. We're not going to use some variable matrices for a little bit. We're going to focus on some matrices with real number entries for the meantime. And let's see what a couple of different properties look like between matrices. We can add and subtract matrices if they are the same size. So let's try out a couple of problems here to get some practice. If we have matrix A, we could say let A equal the matrix 1, 4, 2, 1, and we'll have B equal to the matrix 3, 4, 1, 5. And as we can see, so A is a 2 by 2 matrix, B is a 2 by 2 matrix, so A and B are the same size. That's what we want to check first. And check. Good to go. So now if we want to add these two together, we'll say A plus B is equal to, and then I'll just rewrite them down. We've got our two 2 by 2s here. And it's really simple. All we'll have to do is add the entries together that are in the same corresponding positions. So let's start off. In the first position, we've got 1 plus 3. Moving to the right, we've got 4 plus 4. Then 2 plus 1, and 1 plus 5 in the bottom right corner. And then we just finish up by adding those together, giving us our final sum here. So our final answer, we've got a new 2 by 2 matrix. Notice it's the same size as A and B were originally, and we have our new entries in our final answer. Let's try out a difference now. We'll take A minus B. And again, I'm just going to copy down these matrices again. Likewise, we're just going to subtract the terms in the same corresponding positions now. So now we have 1 minus 3 in the top left, 4 minus 4, 2 minus 1, and 1 minus 5. Giving us a final answer, which again will be a 2 by 2 matrix. Now we've got -2, 0, -1, and -4. There you have it. Addition and subtraction are not too bad between matrices, but let's also take a look now at what multiplication looks like. So if we're talking about multiplication with matrices, they can be multiplied by a scalar value, just a single number, or by one another if the columns of the first matrix are equal to the number of rows in the second matrix. And division between matrices is undefined. So what do I mean by that exactly? If we have two matrices, let's say the first matrix we have is M1 by N1, so these are our rows and columns again, and we're trying to multiply that by M2, a second matrix that is M2 by N2. What we want to have happen here, we want the number of columns in that first matrix to equal the number of rows in the second matrix, so we want N1 to equal M2. And if we look at our outer terms here, our M1 and our N2, we can say the resulting matrix has those dimensions. So our inner values here tell us if the matrices are able to be multiplied together, and our outer two tell us what the actual size will be of our product matrix. Let's take a look at an example for multiplying by a scalar value first. So if let's do one with a scalar. If we have 3 times the matrix 4, 2, 2, 1. It's as simple as it seems. We're just going to take 3 and multiply that by every single one of our entries here. Which is going to get us our final answer. And again, the size remains unchanged for the scalar matrix, but that's not always the case with our products between matrices. Now let's try an example where we're looking at two matrices being multiplied together. So first up, we've got a matrix. I'll do a 2 by 2 here. And we're going to multiply that by a 2 by 3 matrix. And let's see, we've got 2 columns here, 2 rows there. So we have our 2 is equal to 2 for our inner values. Check, we're good to go. So notice these two matrices are not the same size, but we're still able to multiply them together. And what we're going to end up with is a 2 times 3 matrix for our product. So here's how we actually can go ahead and do that. When I go through these, I think it's easiest to start with the second matrix here, and then I'm looking at that first column, and I'm going to take those entries and align them with the first row of the first matrix and multiply the individual entries together. We're actually performing a dot product here, so we want to multiply the entries together with one another, and then we're adding that sum. So what that looks like is we'll take our 2 times 1, and we're going to add that to our 3 times 2 here. And then likewise, we can take this same first column and multiply it by our bottom row here, and that's going to get us our bottom entry in the first column. So we have that 2 times 5. We're going to add that to our 3 times 2. Now we could just keep moving forward to go to our middle column. So now we're in the middle column of our product, and we're going to take those 2 entries and again match them up with the 2 entries in the first row of the first matrix. So we'll get 3 times 1 and add that to 4 times 2. And we'll just keep moving forward here. 3 times 5 plus 4 times 2. And then the last column we'll get 1 plus 1, or 1 times 1 plus 1 times 2. And 1 times 5 plus 1 times 2. Then we just have to combine all of our terms together. And when we simplify this down, we should be getting a final answer of 8, 11, 3, 16, 23, and 7. And notice we've got a 2 by 3 matrix here, just like we said we would based on our initial observation of the matrix size. Now let's take a look at multiplying these two matrices together in the opposite order. So I'm going to put our 2 by 3 matrix first here. And now when we try and multiply these together, we can see the number of columns in our first matrix is not equal to the number of rows in our second matrix. So we actually cannot multiply them together when we flip the order around, and that is because they don't have the same size here. And notice that we're not getting the same solution when we multiply them together this way versus this way, because matrix multiplication is not commutative. It's not the same thing as multiplying two scalar values together where we can flip them around. But with matrix multiplication, the order is unique and it matters which direction we're multiplying them in. So we're just going to say no solution here, and we're going to make a note that matrix multiplication is not commutative. Had they both been square matrices to start off, let's say, like a 2 by 2 and a 2 by 3, we could have flipped the order and successfully multiplied them together, but we would have again gotten a different final product if we're multiplying them in different orders, because that matrix multiplication is not commutative.